given by Olaf Magnussen from the Christian Albrechts University in Kiel in Germany, and he will report on Operando surface X-ray diffraction studies of oxide catalysts during electrochemical oxygen evolution. So please, Olaf. So this is a contributed talk. So please try to stay in time and leave some time for questions. Thank you.
So yeah, hello everyone. So I want to talk today about some of our work we do on oxide catalysts in electrochemical environment. And so this is a joint project my group has with a group of Philippe Ballon and Stuart Maroon at Palaiseau, and funded by DFG and ANR, and that's sort of the experimental team. So what are we doing here? We are using X-ray diffraction method for Operando studies of electrocatalyst interfaces, and in particular of electrocatalyst interface in the potential regime where the surface becomes oxidized or oxygen evolution occurs. And this is actually a larger project. We do different type of work here, and I want to talk today about our studies of cobalt oxide catalysts. I also wanted to originally include magnetite studies on single crystals, but for time reasons I have to skip that. And what we also are doing for about 5 years is we use the high energy surface X-ray diffraction technique Gary was talking about for studies of platinum oxidation and degradation. And actually this technique, and especially the huge amount of CTR data you get by this, gives you really some amazing insight into that, because it allows you to analyze very disordered type of surface oxide structures which you could not obtain, let's say, by a normal CTR type of study. So if you want to get details on that, please check out the poster of Timo Fuchs at P33. Okay, so why are we studying that? Now, you know that the world is striving towards becoming CO2 neutral, and this is the general idea behind it, so that you use electricity to produce in the very end hydrogen, and from the hydrogen you can use it for application in fuel cells, but you can use it also for making all kinds of base chemicals. And in the moment, the hydrogen comes from fossil fuels, but the plan is, of course, to produce this CO2 neutral, which you do by water electrolysis. So that's the so-called green hydrogen, and it's been an area which has extremely grown over the last years. Yeah? So the key issue here is the electrolysis, which is done in a cell where you have basically two electrodes with an electrolyte in between, and at the electrodes, at one electrode, you evolve the hydrogen, you produce OH minus, and then that's an alkaline, and the OH minus at the other electrode is converted in O2. So these are the critical reactions at the interfaces. These are electrocatalytic reactions, and these are reactions at a solid liquid electrochemical interface under conditions where gas evolution occurs. So there are very few surface science methods that can access such type of interfaces and obtain structural data, but X-ray diffraction is one of them, or one of the very few ones. So that's basically the idea. And we in particular study in this project soft pro transition metals like iron, cobalt, nickel, oxide, and oxyhydroxide. And these are very interesting catalysts for the really difficult reaction, which is the oxygen evolution reaction. This is much more difficult than the hydrogen evolution because it involves transfer of 4 electrons. So most of the research in this field concentrates on improving these electrocatalysts. And these are interesting for so-called advanced alkaline electrolysis and also photoelectrocatalysis. Because these oxides are very active electrocatalysts for the oxygen evolution reaction. They have a good stability in alkaline electrolytes, and they are from relatively earth-abundant material. But there's also a problem with them. They usually do not have very good electric conductivity. So you use them in form of thin films and nanomaterials deposited on some good electric conductor. And this, of course, is also a big problem for surface diffraction studies, because you cannot work with single crystals. You can make such single crystals, but very often they have too poor electric conductivity, so that you can actually evolve oxygen on them. So we also have to work with thin film samples, unfortunately. And now the open questions here are, of course, the most important question is what actually is the interface structure of these oxides under reaction conditions. And that's in most cases not really known. And because this interface structure is not known, you of course do not know exactly in detail how the catalytic reaction mechanisms run, because this of course also depends on the exact interface structure. So most of the research in this area is very, let's say, applied. You mix together some materials, see how they work, and if you have a good catalyst, you are happy. But in terms of fundamental understanding, there's still a big lack, and so there's a real need for a detailed studies of a well-defined model system, similar as Gary already introduced in his talk. And so, as I said, my talk focused on cobalt oxides, and in particular, we look at cobalt 304, which is a spinel, as you see here, the crystal structure. This is a very popular material. There are hundreds of publications on oxygen reaction on this materials on it. And here you see a very interesting study by Arno Bergmann from the group of Peter Strasser in Berlin. And they did studies with powder X-ray diffraction and X-cells. And here you see some of the data. So they did measurements at a few potentials, and including one close to the onset of the OER. And there they saw a broadening of these peaks, and from that they concluded that there's a skin layer formed on the surface of this oxide, and when you change the potential back away from the OER, this surface heals again. Bergmann et al. Attributed this change to the direct effect of the oxygen evolution reaction, but we can come to a bit different conclusion, as you'll see afterwards. So, okay, so our approach is to use electrodeposited cobalt oxide films, and we modified some recipes in the literature for producing thick cobalt oxide films, and derived a method by which we can electrodeposit very thin epitaxial films between 5 and 25 nanometer thickness, and they have a well-defined stoichiometry, so we can, depending on the deposition conditions, either deposit cobalt 304 or this layered material cobalt oxyhydroxide, and we can deposit them in a very nice epitaxial way on gold single crystals. And these are the samples we are working with. So this is in principle how these the structure looks like. This is how the surface morphology of the different samples look like. So you can see we can deposit relatively flat and well-defined films. For the cobalt oxide hydroxide, you actually see here the atomic steps in the eighth image of the surface. For the cobalt 304, we see here such islands which are usually flat top, and they are more or less three-dimensional. So we can get some deposits, but they are not ideal. But, and for that reason, we also cannot measure something like crystal truncation rods from them. So we see here in this reciprocal space 3D illustration the gold CTR, but the cobalt oxide, as you can see here, only manifests in such rather broad break peaks. Yeah, so that's what we will analyze in the following. Okay, so we do our Operando XRD studies in a cell, as you can see here, it's a bit similar like this as Gary mentioned. Our cell has the advantage that has here such a bulk of electrolyte on it. We can operate the cell under really vigorous oxygen evolution conditions. So basically, if you look with the camera into the cell, it looks like this is boiling. So much gas is evolved, and still we can do X-ray diffraction studies. And what we are doing is we basically go to one of the cobalt oxide break peaks and then image this break peak with a 2D detector and then change the potential. And when you change the potential, you see that the peak shifts and also changes in width. And this we can do with quite nice high time resolution of below a second. And what you do here is, as you see here in this illustration, is you cut with the EVA sphere through the peak and you project the peak on it, and so you get information about the crystal structure of the small crystallite that constitutes the film in the vertical direction and in the horizontal direction. Okay, so when we do these type of studies for the cobalt oxide hydroxide, we find that they basically for the we see no change. So basically, this is how we do the studies. We sweep the potential first up and then down. This is the electrochemical current that flows here, with a typical cyclic voltammogram, and this is structural data we obtain from that basically simultaneously to the electrochemical data. And you can see here for cobalt oxyhydroxide, the blue data, there are absolutely no changes. And that's what's shown here is the coherent side in the surface perpendicular and in the in-plane direction, and derived from the break peak width. And you see that this is absolutely stable. So this is a actually nice model system. Nothing is changing. It's different for cobalt 304. You see here that at some point here the intensity goes down, and then when we sweep the potential back, it recovers with some hysteresis, but that's mostly a matter of the time. And actually we can go through this curve several times, and it's always right on top of each other. It's very reproducible, and we see this in both directions. So we interpret this type of results as similar as Bergman, as a formation of a skin layer in which the cobalt 304 crystalline structure is converted into some other structure. We cannot find any other break peaks or diffraction intensity, so we attribute this to some either rather amorphous or nanocrystalline type of structure. Okay, this skin layer stays on the surface even if you go deep into the oxygen evolution regime, and here we actually went to current densities of 150 milliamps per square centimeter. So this is getting actually close to current densities used in real electrolyzers. And you can see there are still some small changes if you actually plot this as a function of the electrode potential. You see this is more or less a linear change with potential for the skin layer thickness. So it gradually thickens, and this linear change is similar actually as you find also for many passive films on metal electrodes. We also did at Soleil combined X-ray absorption spectroscopy and XRD measurements. I don't want to go in detail about this data, but from these data, we found that for cobalt 3 or 4, basically the skin layer seems to consist entirely out of a cobalt 3+. Whereas at in the cobalt 3 or 4 crystal structure, you typically have a ratio of 2 cobalt in 3+ and 1 cobalt in 2+. So apparently in the skin layer, all the cobalt 2+ is converted to cobalt 3+ in a highly reversible way. We also find in our X-ray diffraction studies that there are strain changes. They are quite substantial in the remaining crystal structure, and that's only for the cobalt 3 or 4, not for the cobalt oxyhydroxide. And we attribute those to epitaxial strain effect because you form the skin layer and you expect the lattice a bit contracted, and this leads to such strain in the horizontal and vertical direction. The interesting thing now is that samples with different morphology and produced in a bit different ways show this to a very different extent. And here you see 5 examples. The 4 right ones here are electrodeposited samples, and the very right one is a 3D consists of a rather 3D deposit, and this is more planar deposit. And here on the very left in black is actually a film produced by the Libuda group in Erlangen by UHV epitaxial growth. And you see that you have here some samples where there's almost no change in the surface structure, so there's almost no skin layer formation. In some, you find a skin layer that is between 1 and 3 nanometers thick. And now, if you correlate this structural data with the simultaneously measured electrochemical data, you see that the really good catalysts are actually those where you form skin layer. Yeah, you see the red one here. You have a high OER current. When you're here in this black curve for this film, which does not show the skin layer, there's almost no reactivity. And you can do this quantitatively. You can plot either the current, the certain fixed potential as a function of the skin layer thickness, or the so-called overpotential, where you have the onset of the OER, and you see that there's a very clear correlation between the skin layer that is formed on the surface and the reactivity. And interestingly, this is even true in a region where the skin layer is much thicker than just the surface layer, where it's here effectively a few nanometers thick. And that's very surprising, because usually you expect that the reaction on a catalyst surface occurs on the catalyst surface. But what we are seeing is that actually it seems to occur in a 3-dimensional reactive zone, which is the entire skin layer. And that is something we still have to understand in more detail. It may be that the skin layer is actually sort of nanoporous structure. I mean, as I said, we have very little information about the skin layer. We only know how much of the crystalline material is transformed. But we know this transformation is reversible, so it cannot be involve long-range mass transport, I think. And we see, yeah, that it is in the nanometer range, having the nanometer range thickness. So I think this is a very interesting observation. We are working to understand this further, but it may shed some light on how actual OER catalysts really work, and maybe we can derive some lessons from that, how to improve the reactivity of real catalysts. So with this, I'm at the end of my talk, and what I want to show you here is that even if you cannot measure nice CTRs, you still can learn something about the interface structure by such in situ or operando studies of such cobalt oxide electrocatalysts. And we saw that some of the oxide, the oxyhydroxide, had a very high structural stability. So this is actually a nice model system. And because the structure does not change under reaction conditions, and it's also actually a very good catalyst, similar as a CO304. And here actually you form the skin layer, which is probably rather chemically related to this cobalt oxyhydroxide, because the average cobalt oxidation state of 3+ is the same as in this material. It's a reversibly formed phase driven by the oxide thermodynamics, not by the OER itself, because it starts at much more negative potentials, and it seems to be a 3 OER active phase. So this, I hope you got a short insight into what we do with these methods in electric catalysis, and I thank you for your attention, and I'd like to end here.